Hello and welcome to the Superposition Guys podcast. My name is Yuval, and my guests today are Alex Keesling, CEO, and Nate Gemelke, CTO of QuEra, a company building quantum computers based on neutral atoms with a unique analog quantum computation mode. Alex, Nate, and I discuss why they chose a different path towards a universal fault-tolerant quantum computers, the significance of recent qubit shuttling experiments, what they learned from the Amazon bracket integration, and much more. We hope you enjoy this episode. Hello, Alex. Hello, Nate. Thanks for joining me today.
Hey, Yuval. Thank you for having us. It's a pleasure.
Hey, Yuval.
So, Alex, who are you and what do you do?
I am Alex Keesling. I'm the CEO of QuEra Computing. We're a Boston-based startup building quantum computers with neutral atoms and the rest of the stack that goes with it.
And Nate, how about you? Who are you and what do you do?
Hey, you're starting with such deep and difficult questions. I'm QuEra's CTO.
All right. My understanding is that QuEra is building a quantum computer based on neutral atom technology. There are obviously other companies who are using neutral atoms for their quantum computer. What's different about your approach?
Yeah, I think that's a great question. We, as you say, are building quantum computers using neutral atoms. Our atom of choice for this is rubidium. It's something that we have carried over from QuEra's beginnings as an effort that spun out of many years of research at Harvard and MIT, where we developed this platform and we found rubidium to be an excellent candidate for this. So this is one of them. The other thing is that we're really focused on creating efficient tools for quantum computers that provide the most useful value both now and at every point along the evolution of the technology. So our first generation of machines is using an analog computational mode that is different from many of the other quantum computing players. We are using fewer controls, but going to larger system sizes and particularly focusing on finding the applications that have an efficient encoding in the hardware as it exists. So we leverage the flexibility of being able to reprogram effectively the connectivity of our quantum computer every time we run a program.
So, Nate, maybe you could help decompose this for me. So, first, congratulations. I think you just launched the computer on the AWS bracket, and it has, I think, 256 qubits. Is that qubits as in the gate-based qubits? What does analog mode mean, and what kind of problems can it solve?
Yeah, I think obviously this is a new machine, and you do have to understand its strengths and weaknesses pretty carefully. We're calling these things analog Hamiltonian simulators right now, and the way that this machine works is you can put any number of atoms that you want up to that 256 and position them anywhere that you want on a plane and set up a calculation with a new register basically every time you run a calculation. And, beyond that, obviously you want to process quantum information. So the way that we do that is we drive the atoms between states, ground state of the atom and the excited Rydberg states. And when they're in the Rydberg states, they like to interact when they're close by. So, that's essentially the mode of operation of the machine, is that you program the position of the atoms, you fix them while you run a pulse sequence, and then run a calculation that way. So it's a little bit different from gate-based computing, where you're really running, a unitary targeted on like single qubits and pairs of qubits at a time. In a way, you're doing operations on the whole array at once, and using this programming of the positions and the timing of pulse sequences to your advantage. It's a really great tool for doing a few things that we know about today, and probably some things that we'll find out about as people log on and start playing with it and trying things that even we didn't expect. But we do know that it's really good for doing things like quantum simulation, like looking at materials problems and looking at other kinds of quantum systems and trying to simulate what they do by arranging the atoms in the right way and doing pulse sequences in the right way. It's also really good for doing things like optimization problems. doing things like finding independent sets and graphs, and we have some work on that, and have exposed the computer on the cloud in a way that you can run algorithms like both of those kinds of things.
Let's assume for a second that you were not with QuEra, but you were advising a commercial customer. So commercial customer has an AWS account, goes to Bracket, sees a whole bunch of quantum computers, the D-Wave and IonQ and QuEra. When should they use QuEra? That's question number one. And two, how do I program the machine? Is it just Qiskit, like I program an IonQ machine, or is it something else?
I guess that one's to me. Yeah, being that it is not a gate-based computer, Qiskit is not a particularly great fit for that. We have a relatively simple intermediate representation that you can use to program the machine that's really based around what it can do. So what you'll find there is an ability to move the atoms around in space and pulse sequences in time. And that's kind of the natural mode of operation for the machine. Now, over time, we will, improve the capabilities of these machines, and we will roll out new features that look more and more like gate-based machines as well. And as that happens, I think you'll see a melding of the languages that you use to program it.
Do you see the future as hybrid, analog, digital quantum, or ultimately it's just going to be a fault-tolerant, universal gate-based machine?
Well, I think everybody is waiting for the day that it's a fault-tolerant machine, and we're not just waiting; we're trying to make it happen here. So ultimately, I do believe that that's what we'll see. But in a lot of ways, hybrid analog and digital is a step along the way, probably. There's a lot of different meanings behind the word of hybrid, of what different things you bring together to do that. There's also hybrid computing, where you bring classical resources and quantum resources together. I think that will be a step along the way. And as those things become successful, I doubt that we will leave them behind after we've seen success with those. So I think, in the end, I doubt that quantum computing will be exactly what everybody imagines today. I think there will be surprises along the way. I think that's, the best reason to build computers now and get them online, because we're going to find those surprises. And I think having the vehicles to do that and putting them in, basically the whole world's hands, that's the recipe for success for us all. And, let the surprises begin. Once they begin, I don't think that we're going to leave them behind either. So I think we're going to see aspects of all of those things, at the end of the day, when we really have these machines in our daily lives.
Alex, I think that you were part of the original team at Harvard that developed a lot of this technology. And I saw some recent articles about qubit shuttling. And could you put it in context of where this kind of technology would lead us?
Yeah, absolutely. Yeah, I must say that it was a very exciting time when I was doing my PhD to be developing this platform and really see the amount of progress that we were able to make very quickly. We started talking right now about analog processing and Hamiltonian simulation, and this is one of the strengths of the platform: the fact that we can move atoms around even just to initialize the connectivity of the processor, and this has allowed to encode problems very efficiently. Now, the next step in the technology is taking that idea further. And the recent results that you're describing, the very exciting thing about this is that it has allowed us to look at this platform as a viable way to also do gate-based computations in a way where part of the programming is to reconfigure the chip in real time, meaning that we can encode information in the internal state of our atoms and then move them around to reconnect them with other ones. This, in the published work, was a way to very efficiently implement things like quantum error correction codes, where just using these tools, we saw that it is possible to move very quickly between different kinds of applications, including a hybrid analog digital, where you do some part of the computation in an analog way, and then you do a post processing using gates. You can even do pairwise interactions between atoms that were far away during the analog evolution. And taking these ideas further, I think shows us that there's a path to scalability. When we talk about neutral atoms, we very often talk about how easy it is to increase the number of atoms in the processor, given that they don't necessarily repel one another, where everything is done using lasers. But there's another consideration to scaling up the size of quantum computers, which is how many controls do you need, and effectively how many controls do you need per qubit. And what we're looking at in terms of the evolution of the platform is to continue to increase the number of qubits that we can use within this gate-based approach. But by virtue of being able to move atoms in and out of different regions, to keep the number of necessary controls low, to continue going to larger and larger useful qubit counts.
And does that also allow you to do essentially mid-circuit measurements, move qubits to a different region and just measure a few of the qubits without interfering with the rest?
Absolutely, that's one of the things that we are looking to enable. Having a region that allows to read out the ancillary qubits, for example, for quantum error correction protocols, and also the ability to bring in fresh qubits into the computation.
Nate, I wanted to ask you, why aren't other neutral atom companies following the same path? Is the path of delivering analog quantum computation perhaps make it longer for you to get to sort of the holy grail, the universal gate-based fault-tolerant computer, or do you see it differently?
I don't want to speak for others, but I will say that I think putting out actual products that are analog now allows us to kind of take a pathway to the ultimate goal, which we talked about it before, is fault tolerant quantum computation on a kind of different pathway than I think most people think about on a daily basis. Usually people work to make small systems that are fully programmable, and then scaling is a game of with a fully programmable computer, making it larger and larger. So what we've chosen to do a little bit differently, if you kind of think about our pathway on a plane, where one direction kind of signifies the programmability of the device, and the other one signifies the scale. We've gone to make the scale as large as possible first, and then improve the programmability later. What that lets us do is put out a first product that very clearly there's nothing on Earth that can tell you what it's going to do. You just have to run the machine itself. And that's something special. That means that machine is unique on Earth. And at every step along our pathway, we can continue to make a machine that you just can't predict what it's going to do. And that's what the age or the era of discovery really means in a technology arc, is that you're really learning new things with every product that you release. And in this case, we're learning that on behalf of the world. So I think it's an exciting pathway. Definitely, it's the right pathway for me personally, because I like to take my cues from nature about how to build the right technology, and the only way to do that is ask nature itself.
So that sounds a little bit like the Feynman quote, right? Or was he referring to gate-based machines?
Well, I think honestly, my personal read of what Feynman said, and I'm definitely an older guy than Alex is, but I wasn't there to hear it in person. I've only read it, but my read on what Feynman has said is very close to the heart of building quantum simulators, and I think, in fact, there's a line in what he said at one of his lectures that basically describes a neutral atom machine verbatim, just representing every qubit with a single spin in an atom. So I'm proud to have delivered on the dream that I wasn't there personally to hear, but could read in print.
Alex, could you tell me a little bit about the company? How large is the company? How much funding? When was it started? And anything you can share?
Yeah, the company, as I was alluding to earlier, the company is the result of work at Harvard, where in 2019 we had accumulated enough evidence that these neutral atom systems were powerful enough to deliver on a promise of having quantum systems that could do something useful for at least us at that time. And that was when the company was put together. The company since then has been structured in a way that really takes a holistic view at quantum computing, and allows us to work with what are the ways that we can extract the most value out of near-term quantum computers as we build towards this longer term of fault-tolerant quantum computers. And that's a reason why the company has people working on hardware, commercializing the developments initially from the universities, but now developing them further. We have an engineering team that is taking these machines to a different level than what has been done in academic settings. We have, of course, a drive to bring these machines to customers and to provide something to them, to learn from them. And we have a group of software developers that are building tools for them to both access the machine, but also learn how to program the machine and how to get the most out of it. And last but not least, we have a group of application scientists who are interfacing with customers and working with them on how do we take the problems that they have and convert them into things that we can run on the hardware now. And how can we reduce the overhead in implementing all of these algorithms? This we think is crucial, especially for the next few years. Going back to what Nate was saying, we really want to discover what are the best applications for quantum computing. And for that, we need to be very conscious of using the quantum resources that we have efficiently. So that kind of forms the full stack. At this point, we have about 40 people. We've been very successful at growing a fantastic team of very high quality people that are all motivated to bring this dream of useful, practical quantum computing to fruition.
When you think about the AWS bracket integration, now that you're on the other side of it, what advice would you give to someone who's just built a computer and wants to go through that process?
Oh, there's a lot there to say, but I think that it's something that we always felt was very important, was to keep in mind who are going to be the customers, who's going to be using the machine, and how, and really focus on what are the use cases that we expect to see, at least in the early stages of access to the technology, by talking to potential customers, and develop things like interfaces and intermediate representation that Nate discussed, with that in mind, by getting that constant input from others. That, of course, comes with working closely with the team on the other side to make sure that we are working together to define standards, to always put the customer in front and figure out how do we align on connecting our part of the technological stack with the service that they're offering, and also work together through how are we going to get our message out there, and how are we going to make sure that we're letting people make the best use of our machines.
Right. Alex left out figuring out where to get pizza at 3 a.m.
How do you feel about the state of quantum hype? Do you think there's too much hype? Do you think there's not enough of it? Where does QuEra stand on the hype scale?
I think that I'm very excited to see how much excitement there is behind quantum computing, because I think that it will be an absolutely revolutionary technology. I think that recently I've seen more of an effort to focus on benchmarking and really creating clear expectations of where the technology is and where it's going in the future. I think that there's a danger in hype getting out of control, and I think that also here at QuEra, this is something that we think about constantly, right? We want to make sure that people understand the promise of quantum technology, but that they also understand where we are right now in the stages of technological development. There are absolutely applications where we expect that these machines, the existing machines, are going to provide something very valuable in understanding how to program them, and understanding how the evolution of these machines is going to bring more and more power to computational tasks. But I think that we still need to work very hard on doing the right matching of existing capabilities to problems that we want to solve. And for us here at QuEra, this is exactly what led to the decision of having our first machine be work in an analog processing mode, because we have seen that from the work that university groups around the country and the globe have done, this is a very powerful way of using quantum resources in a way that has the power to provide answers and insights that are very hard to replicate with classical solutions.
So, as we get close to the end of our conversation, I wanted to ask you, Nate, and then Alex, what quantum person, dead or alive, would you like to have dinner with?
Dead or alive? Well, that runs a risk. Can we just stick to dead so that I don't have any apologies to make afterwards? I'm going to take that as a yes. So I have to say, I grew up in physics reading Lev Landau comics, also known as the course on theoretical physics. It's sitting across from me now, and somehow I just feel that I think Lev Landau actually died the year I was born. So we have a certain kind of soul transference or something happened. So I think that's my answer.
And Alex, how about you? And by the way, I know that you could always say dead and alive, but let's leave the superposition out of it for now.
I'm still thinking about who a quantum person is and what that looks like. I don't know. There's just so many. I guess the easy answer is to say Feynman, right? I mean, there's just so many insights that came from him, and the information that you can find about him. He was such a great conversationalist, quantum or not, just a fun person to be around. But I don't know. I mean, there's some of the people alive right now are fascinating to have conversations about what the history of this field has been, right? And I think that's the thing that's, to me, so exciting about working in this right now, that things are moving so quickly, so much so that things that are, are seen as the historical progression of quantum computing were developed by people that are still around and are still active. And, of course, there's Peter Shor, there's Umesh Vazirani, there's just so many people out there that are, picking their brains is amazing. I'm gonna simplify it and say Feynman. He looks like a great guy to hang out with.
So, how can people get in touch with you to learn more about your work, and what type of people would you most like to hear from?
People can get in touch through our website. I hope that they're also going to the Bracket website and start using our machines. Who do we want to hear from? Anyone who has great ideas, both about what they want to do with our devices, about where we should be moving the entire ecosystem towards. People who are excited about joining forces and working together to make sure that this quantum computing adventure is successful.
Perfect. Well, thank you so much for joining me today.
Thank you, Yuval. Have a great one.
Thank you so much.